So last time we started with section 6.1, which is on sample spaces, experiments, events, and stuff like that. Let's just do an example. So flip a coin and roll a standard six-sided die. So we flip a coin, we look at the outcome, we roll a die, we look at the outcome. Remember, the sample space is the set of all possible outcomes. So in this case, and remember we use S to denote the sample space. In this case, the set of possible outcomes are, it can be heads and 1, heads and 2, heads 3, heads 4, heads 5, heads 6, or it could be tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Meaning, like, you know, for the coin, it can be either heads or tails. For the die, it could be 1 up to 6. And so these are your possible outcomes, and overall, right? So, okay, so remember an event. An event is technically a subset of the sample space, but usually events can either be written, an event can be written like in set theory notation or just in plain English. So let me write an event in plain English. So let E be the event that the die roll is at most 3. Meaning, yeah, so when you roll the die, let's say we're taking the event that it's at most 3. And so a very standard question you could be asked is to list the elements of the event E. Okay. When you're asked a question like this, you'll basically, what it's trying to say is, write. So here I've described E in plain English, and it's asking you to write the event E as a set, right? So remember, E is supposed to be a subset of the sample space, and basically, it's the event that the die rolls at most 3, so it'd be like H1, H2, and H3, T1, T2, and T3, but not any of those outcomes, right? So H1, H2, H3, T1, tails in 1, tails in 2, tails in 3. Right? Is it clear how I came up with that? So, yeah. So basically, you want to write down all the outcomes where this condition is true. So where the die rolls at most 3. Okay, now I can say let F be the event that the coin flip is heads. So So then you could be asked, list the elements of E, well, I'll say just to be clear, this is an event. So of the event, E intersect F. So can anyone see what the elements are? Yeah. Yeah, exactly. So, right, because here was intersection, we have to remember intersection means and. So we're looking at the event that E occurs and F occurs. E means that the roll is at most 3. F means that the flip is heads. So, if I say E occurs and F occurs, it means the coin flip is heads and the roll is at most 3. So that should be H1, H2, and H3. Because it's saying that the flip is heads and the roll is at most 3. Right? I mean, you could also be asked, like similarly, you could be asked, explain or describe the event E intersect F in words, right? But then basically it would be what I said, like it's just the event that the coin flip is heads and the roll is at most 3. The dice roll is at most 3. Okay. Actually, okay, let's say, suppose I said describe. So E intersect F complement in words. Can anyone see what that is? Yeah. Well, that would be if I asked to list the elements, that would be correct. But okay, maybe it's not clear what I mean by in words, but yeah, maybe a more clear thing would be, in plain English. So not using set theory notation. But that is the right set in the end. Yeah, so maybe, yeah, there might be a cleaner way to phrase it, yeah? Yeah, or you could say, yeah, or again, there's a million ways to say it. So you could say, yeah, the die roll is at most 3, and the coin is not heads, or you could say, because we know not heads just means tails, so the die roll is at most 3, and the coin flip is tails. But either way, you could also say the die roll is not bigger than 3, and the coin is, not heads or something. I mean, there's a lot of different ways you could say this, but yeah. Okay, any questions about that? But yeah, a simple way to say it is, yeah, the die roll is at most 3, and the coin flip is not heads. That's probably if you just read this out, that'd be the easiest way to think of it. Okay. So let's say, let me introduce another event. So let G be the event that the die roll is a 6. Okay. So for this event, for these two events, so E is the same event as before, and G is this event, what would be the intersection of these two events. Yeah. Yeah, no, not quite, because, yeah. Yeah, it's going to be the empty set. So there's, right? There's nothing in common, because it's impossible for the die to roll at most 3 and 6 at the same time, right? 6 is bigger than 3. So this is like the event that when you roll the die, it's at most 3, and simultaneously it's equal to 6. But that's just not possible, right? So in this situation where where two events have empty intersection, so okay, when two sets have empty intersection, we introduced this terminology along, last week or something. We said the sets are disjoint. When we're talking about events, there's a slightly different terminology we use. So we say that they are, when two events have empty intersection, we say they are mutually exclusive. Okay, and that just means those events cannot happen at the same time. They cannot both occur. So if you're asked on a test or something, are these two events mutually exclusive? Then the question it's asking you is, do they have empty intersection or not, basically? Okay, so let's move on now to section 6.2. Okay, and this is on assignment of probabilities. So far we've talked about events and outcomes and stuff like that, but we're supposed to be talking about probability. So, basically now the probability part comes in where we start talking about, what's the probability of this event happening or that event happening and things like that. So in general, suppose you have a sample space for some experiment, and suppose it's like, just to give an arbitrary labeling to the elements, let's say it's S1, S2, up to Sn, the capital N. So this is just saying we have an experiment where these are your possible outcomes. So let P1 be the probability of outcome S1. Similarly, P2 is the probability of outcome S2, and ... Pn, let Pn be the probability of outcome Sn. So I'm just saying, when you do the experiment, the probability of S1 is P1, the probability of S2 happening is P2, and so on. So there's a few special properties that probabilities have to satisfy. So these are kind of two fundamental properties of probability. Okay, so the first one is that for everything in your sample space, the probability of it has to be positive. So Pi is bigger than 0 for all I, meaning, so this I is just an index. So what I mean is, for all the different P1, P2 up to Pn, they all should be positive, right? And that's because the sample space is supposed to be the set of all possible outcomes. If the probability of something in your sample space was 0, then it wouldn't be a possible outcome, right? If, when I roll a die, the probability of getting a 7 is 0, so 7 wouldn't be in the sample space. And similarly, you can't assign a negative probability to some outcome. That wouldn't make any sense, right? If I say the probability of this is -1, that would be kind of crazy, right? So probabilities for everything in your sample space should be positive. And the second property is that if I add up, so if I add up P1 plus P2 all the way up to Pn, it should equal 1. Or in other words, if you like summation notation, it doesn't really matter how you write this, but if I sum from I equals 1 to n, Pi, it should equal 1. These are just saying the same thing in two different ways. Okay. All right, so if the probabilities didn't add up, so it wouldn't make sense to have probabilities add up to something bigger than 1. If they added up to something less than 1, that would also be weird, because that would say with some probability none of the outcomes happen. But what does that? Yeah, what would that even mean? That wouldn't make any sense. Yeah. So this is just saying this is just summation notation, meaning this is just summing up the values from 1 up to n. So this thing is just saying exactly the same as this thing. But you don't really need to worry about this notation. If this is more clear to you, then this is what we're talking about. Adding up the numbers, it should equal 1. Any other questions? Yeah, Pi, this is just saying really what this thing is saying is also the same as saying P1 is bigger than 0 and P2 is bigger than 0 and ... up to Pn is bigger than 0. Yeah, no. I here is just standing for index. So for every index, it's also. Yeah. Any other questions? Okay. Okay, so like a really, really simple example is the coin flip, right? Flip a coin. You've got two different outcomes. Heads or tails. Each of them has probability 1/2. Right, so here, this would be like, S1 is H and S2 is T or whatever. I mean, and P1 is a half, P2 is a half. So you can see this satisfies the properties, right? All the probabilities are bigger than 0, and they add up to 1. Okay. Actually, generally, often it's going to be convenient to write like probabilities in terms of these kinds of tables. So this kind of table is called a probability distribution. Okay. So for example, if you're given some experiment and asked, please write down the probability distribution for this experiment, what you would do is you list all the outcomes on the left side, you list all the probabilities on the right side, and yeah, just make sure you compute them all correctly. If you want to double check things, like they have to satisfy the properties, so everything here should be positive, and everything here should add up to 1 if you add them all up, right? That doesn't necessarily mean your distribution's correct, but if these don't add up to 1, you know 100% certainty your answer is wrong, right? But, okay, any questions about that? Okay, so we've kind of been talking just about probabilities of outcomes, right? But what about probabilities of an event? So an event, remember, is a subset of your sample space, which may contain many different outcomes. And it turns out it's not hard to compute the probability of events if you know the probabilities of the outcomes, because you just add up all the outcomes in that event. So meaning, so let E be an event. And suppose maybe E is equal to x1, x2, up to xk. The probability of the event E is then defined to be, so the notation is PR of E. And to compute the probability of E, you just add up all the outcomes inside of E, like you add up all their probabilities. So the probability of E is the probability of x1 plus the probability of x2 plus dot, 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 up to the probability of xk. So let's do an example to see how this works. So suppose I roll a red die and a yellow die. Let E be the event that these two dice rolls add up to 6. Right? And then you can say, what is the probability of that event? Okay. And obviously, if you're not told any specific things, like you should assume these are six-sided dice, right? Six-sided dice. They're fair dice and whatever. Okay. So let's first start by thinking about what is the event E. Like, what are its elements? So I'm going to write this like, so to get a 6, you could get a 1 and a 5, right? You could get a 2. So when I say 1 and a 5, I mean a red 1 and a yellow 5, or a red 2 and a yellow 4, or 3 and 3, or 4 and 2, or 5 and 1, right? There's all those possibilities. So E is the event 1 and like 1 in the red and yellow 5, 2, 4, 3, 3, 4, 2, 5, 1. So then the probability of E should be just what you get by adding up these probabilities. So it's the probability of seeing 1, 5, plus the probability of 2, 4, plus probability of 3, 3, probability of 4, 2, probability of 5, 1. Is this clear so far? Yeah? Well, yeah, because, I mean, I kind of see what you mean, that like I've got a 1, 5 and a 5, 1, and this is kind of different, but yeah, I guess, you know, if you roll a 3 and a 3, like let's say I roll a red 3 and a yellow 3, that's the same as rolling a yellow 3 and a red 3. So I shouldn't really count that twice in some sense. So like I'm kind of thinking of these two things, for example, 1, 5 and 5, 1, they're not the same event because this is like a red 1 and a yellow 5. This is a red 5 and a yellow 1. Those are different things. But if I have a red 3 and a yellow 3, that's the same thing as a yellow 3 and a red 3 or whatever. Yeah. Well, but that's not really, it's not really kind of thinking of your outcomes in the right way in some sense. Like, we're not, okay, we're not, I kind of get what you mean, but that's not really thinking of it in the right way. So, you know, we're rolling these dice at the same time. Like we're not then saying, okay, then I'm going to randomly reveal one and then reveal the other, or reveal this one and reveal that one. And we're not thinking of those things as different things, right? If you see a red 3 and a yellow 3, that's just what you see. That's one outcome, you know. See, there's no second way of interpreting a red 3 and a yellow 3. Yeah. Yeah, there's no kind of order between red and yellow that's also being taken into consideration. It's just, you just roll them and you see them. So that's just one outcome, but these are different outcomes, right? Because this is a red 1, and that's like a red 5. But yeah, these things can mess with your head. You got to count these things correctly. Okay. So if we trust that part of it, then hopefully it's clear that this is just by definition of how I compute probabilities of events. And now we need to compute like what is the probability of seeing 1, 5? That's not completely obvious here. I mean, So before computing these probabilities, let's take a little step back. Let me ask, what is the size of the sample space? Yeah. We have to remember what sample space means, I guess. So I'm not just taking, so that would be, N of E would be 5, right? But E is not the sample space of the experiment. Yeah. Yeah, it'll be 36. So you get that from 6 times 6, right? So the sample space is not the event, right? The sample space is all the possibilities, and the event is a subset of the possibilities. So the sample space is size 36 because there's 6 choices for the red one, 6 choices for the yellow one. So this is for the red and for the yellow. And okay, so if you think about it, though, all of those different possibilities should be equally likely, right? So seeing a 3 and a 3 has the same chance as seeing like a 1 and a 5, right? Or a 2 and a 2, or a, you know, all these different outcomes. So I've got 36 possible outcomes. All are equally likely. Yeah. It's still just the same thing, yeah, yeah. So seeing like a red 3 and a yellow 3, like when I roll a dice, this has a chance of 1 over 6. That has a chance of 1 over 6, right? And it's the same as if I saw a red 2 and a yellow 5 or something. You know, that has a chance of 1 over 6, that has a chance of 1 over 6, right? So if all the possibilities are equally likely, then every different outcome must have, you know, if they're all equally likely and the probabilities add up to 1, then everything must have a probability of 1 over 36. So every outcome has probability 1 over 36 because there's 36 different outcomes. All of them are equally likely, but the probabilities have to add up to 1. So they must all be equally, like they must all have that probability, right? So therefore, this should be 1 over 36, 1 over 36, 1 over 36, you know, so on and so forth. So this should be 5 over 36. If you're really kind of questioning this, you could write down all of your outcomes and kind of convince yourself of it, right? Your outcomes are 1, 1, 1, 2, 1, 3, and so on. And all of these should have like a 1 over 36 chance of happening. And you will get exactly 36 outcomes. And if you think about it, yeah, seeing a red 3 and a yellow 3 is the same chance as seeing a red 2 and a yellow 5. Right? Okay. Any questions about that? This stuff is tricky, so do ask questions because if you're wondering about something and something seems unclear to you, it's probably unclear to like 10 other people. So, okay. This is from last time. Okay, so now let me tell you about another thing about probability, which connects back to something we did in chapter 5. So remember principle of inclusion-exclusion? So PIE means principle of inclusion-exclusion. So that was about when I look at the size of two sets, right? The number of elements in A union B was equal to number of elements of A plus number of elements of B minus the number of elements in the intersection. So it turns out there's a similar thing for probabilities. If I have two events, the probability of the union is equal to the probability of E plus probability of F minus the probability of the intersection. Okay. So if you remember this formula, it's pretty easy to remember this formula, right? It's the same thing, but with probabilities. I don't know if it has a good name. I kind of feel like you might just say by inclusion, exclusion, or if you want to be more specific, inclusion, exclusion for probabilities or something. However, if the textbook might say something, if it does, then if it has a name for it, then that's the right name. I don't know what the name is, though. Okay. So let's well, let's look at this this example again. So E is the event that two dice add up to 6. And let's say F be the event that the two dice roll the same, number. Well, first of all, what if I was to list the elements of F? What are the elements? Yep. Yep. So it's all the ways of having two. So it doesn't matter which order I put these in, right? The order, so I'll do it in a wacky order. So it's just all the ways that you could have the same number on both the dice. Okay. Yeah, if you're confused by why I've listed it in this way, there's no good reason. I just wrote them in a weird order. Okay, so now we can, well, let's try to compute this. So probability of E union F is probability of E plus probability of F minus the intersection. So this one we already computed is 5/36. Does anyone see what the probability of F would be? Given that we've, oh, sorry. Yep, because, right, you got 6 possibilities here. They're all equally likely. So 6/36. Can anyone see off the top of their head what E intersect F, what the probability of that would be? Yeah? Yeah, 1/36, yeah. Right, because what are the elements of E intersect F? Well, there's only one of them, right? The only way to have two numbers that add to 6, which are equal to the same number, right, is 3 and 3. So this is the, E intersect F is just the set containing the number, or the outcome 3, 3, right? So there's only one outcome over 36. And so this should be 10 over 36. Okay. And to be honest, if you take E union F, if you list all the elements, you're going to see that there's 10 of them, right? So, but using this formula is a faster way to compute this than to try to list everything. Okay. Any questions about that? Okay, so sometimes in these types of things, you'll have like a, kind of, what's the right word, empirical data or something, data that you get from doing a sample of, people or whatever it happens to be. So let's say that you've got 200 students, for example, are surveyed. And asked what their favorite subject is. Okay, and suppose you get these results. Okay, there's too many subjects to list, so let's just imagine there aren't so many. So let's say math, biology, philosophy, and other. So number of students. Obviously, math is very popular, 120. 10 for biology, let's say 40 for philosophy, and 30 for other. Okay. I'm not that big of a fan of biology. Maybe some of you are. Yeah. Okay, so then you can, from that, you can compute the relative frequency of each outcome. What I mean by relative frequency is like what percentage of people picked math, what percentage picked biology, and so on. And so if I want to compute the relative frequency for math, I take 120 divided by the total number, which is like 0.6. For biology, it's 10 divided by 200, which is 0.05. Here I've got 0.2, right, and 0.15. I think. Yeah. So here I'm just taking whatever number I have here and divided by 200, right? Notice these numbers should add up to 1, kind of like probabilities. So these kinds of things, these are sort of used like in practice as kind of representing rough, like approximate probabilities, right? If you sample 200 students, if 60% of them liked math the best, you might think, okay, maybe the whole campus will have roughly 60% of people choose math if you sampled these, kind of randomly from the population. But yeah, but these are not kind of true probabilities, you know, for necessarily. However, I mean, in some sense, they can be thought of as probabilities. So now imagine I pick a random student not from the whole campus, but just from those 200. So pick a random student from those 200 and ask them what is their favorite subject. What's the probability that they say biology? Yeah, 5%, so this number here. So these can be thought of as probabilities because they are like the probability if I chose from this sample a student and asked them the question, as long as they didn't change their answer, you know, you'd have 5% chance that they say biology. So yeah, so if I pick a random student from these 200, then the probability of the outcome that, you know, or for example, let's say the probability that they like biology or philosophy. When I say like, I mean that biology or philosophy is their favorite subject, right? Then you would have, you would just add up these two things and get, right, 25% chance. Okay, any questions about any of this? So we'll continue this next time and look at sort of how you can use Venn diagrams to compute probabilities. But